Okay, so question 51A, what is the equilibrium constant of a reaction that's carried out at 298 K with delta H of 20 kcal per mole and delta S of 25 times 10 to the negative 3 kcal per mole per Kelvin? First things first, the book made a mistake. The book doesn't have this delta S term as 25 times 10 to the negative 3. It only has it as 25. So if you just use 25, you're going to get an incorrect answer. So just go ahead and proceed with 25 times 10 to the negative 3 kcal per mole per Kelvin as the delta S naught term. Okay, so this is actually a pretty easy equation or a pretty easy problem. It's just basic plug and chug. Any issue you have is probably just going to come with a math error somewhere along the line. It's a very simple math error, which can be annoying, I understand. But overall, it's a simple plug and chug. Okay, so first things first, we're given delta H and delta S, but we know, according to this delta G equals minus RT ln K equation, in order to get the equilibrium constant, we need to have everything in terms of delta G. So we can get delta G, but we have to have delta H and delta S, which we happen to have up above. And we also have the temperature, so 298 K. So if we go ahead and plug everything into the equation, we're going to be able to calculate delta G. So delta G is going to equal delta H, which is 20 kcal per mole. And we're going to subtract the temperature, so 298 K. And we're going to multiply that by delta S, so 25 times 10 to the negative 3 kcal per mole per Kelvin. I'm actually going to redraw this per mole differently. Let's put this up here like this per Kelvin. Okay, and we can see now that our Kelvin terms, our temperature terms are going to cancel out, and all we're left with is kcal per mole, kcal per mole. So we'll go ahead and calculate delta G in this. So if you pull out your calculator, take a second and try to calculate the delta G and then check your answer. Okay, so you should have, after you did the maths for all this, delta G should equal 12.5 or 55, depending on how far you want to pull it out, kcal per mole. Okay, so that's our delta G term, so we have that solved. So now we know R. R can be found in your book, it's just the gas constant, and this R term is going to be equal to 1.986 times 10 to the negative 3 kcal per mole per Kelvin. So kcal per mole per Kelvin. Okay, so that's our R term. So we know the R term, we know RT. So let's go ahead and take this R term and plug it in to our delta G equals minus RT ln K equation. So I'm just going to take this guy and we're going to put him in parentheses for our R, put the negative there, and we have a T of 298K, so 298K, and then we have ln of the equilibrium constant. So don't get this K right here mixed up with this K, this Kelvin. This is not a temperature term, this is an equilibrium term. Okay, so we know 12.5, so let's go ahead and actually move this over a little bit. This guy move it over. So this is going to equal 12.5 kcal per mole. Okay, so now we know we can again cancel out this temperature term, this K, this Kelvin, and our final answer is going to be kcal per mole, and then we can solve for the equilibrium constant. Okay, so let's go ahead and take a second, pause the video, see if you can solve that equation. Okay, so you should have gotten this delta G term is going to be equal to negative 0.592. Just going to round up. And this is going to be still in kcal per mole. Okay, and then we multiply again by ln K. Okay, and again, so this is the same as it was above. So just copy and paste. And we'll see now, in order to get ln K, we have to divide the left-hand side of the equation by the right-hand side, which means that these kcal per mole terms are going to cancel out. Okay, so because the kcal per mole terms cancel out, we're going to end up getting a unitless term. Okay, so pause the video and try to solve for that. Okay, so now on the left-hand side of the equation, we're going to have a minus 21.1 term, and this is going to be equal to ln of k. Okay, so now all we're going to do is raise e to the x on both sides, so e to the minus 21.1. We're going to do the same thing to the right-hand side of the equation. And what we're going to have happen is we're going to get e to the minus 21.1 is going to be equal to our equilibrium constant, or KEQ. Okay, so now all we have to do is a simple plug and chug, and we're going to get, if you plugged everything correctly, a KEQ of 6.86 thereabouts times 10 to the minus 10. Okay, so don't get too terribly hung up if you didn't get 6.86 exactly. The important bit is the 10 to the minus 10 bit. So your calculations might be slightly different than mine in how you round it, but the important part is that no matter how small this 0.86 term is, it's really, 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 really small number. So let's put this into context. What are we saying? So we're saying that if we're doing a reaction and we have, A or compound A, and it's in equilibrium with compound B, which side of the equation is favored? So in this KEQ term is basically really, really, really small. So all it's really saying is that this equation is going to lie way far to the left and not very far to the right at all. So it's the reactants in this case are going to be favored, and the products are not. Okay, and that makes sense in terms of our delta G. So delta G, this is a positive term, it's going to be endergonic, which means this is an unfavorable reaction at equilibrium. So the delta G term matches up with our physical representation of how this reaction should go. So that's the correlation between the KEQ being really small and the delta G being really large and positive.